What we do in the data analytics group at Merle is we try to take data and make sense of it in some way. So whether that's building a new model of that data to predict something in the future, or whether that is trying to find a model of the data so we can tell when it changes. So in this case, what we're presenting here is an algorithm that is able to find pattern matches and a multiple number of pattern matches quickly in data. And this is an application that we built to perform this search and to display visually back to the user the results of the search. And what you can see here at the top is the whole data set that we're going to be searching. This is a synthetic data set made up of a million data points. Under this data set, what you see is a small window. And this window represents the size of a pattern for which we're going to be looking. And here you see just a small snapshot of the big data. And what this window is meant to do is illustrate how difficult it would be to find a pattern in this data. So as an example, let me click here and show you. Every time I click, you'll see a different pattern. But there's a million data points. So if I scroll through, it would be very difficult to find any one pattern that you're looking for. So what we did is we actually allowed the user to draw a pattern here. So I'm going to draw a pattern at the bottom, and to compare it to that snapshot of the data here. So as we drag this along, you can see a comparison of the pattern that we want to find and the pattern in the data at that instant. What our application does, actually, is it takes a number of matches that we would find. In this case, we have 10 matches. And it searches in that 1 million data points. So I'm going to set this to be a pattern of approximately 7 minutes in size, which is about 400 data points. And then when I click search, you're going to see the algorithm search through the million data points. So here on the bottom on the right-hand side, you'll see the performance of the algorithm. You'll see our algorithm's performance in seconds, the world's best algorithm, which is actually only able to find one match, repeated 10 times in a loop, and then the brute force method, which means that we're going to check every possibility for a match. And you'll see when they finish. So you'll see our algorithm finish first, then the world's best method, and then finally the brute force search. And in the middle of the screen, you'll see the results of that search. And you see right away that our algorithm has already finished in 2 seconds. And the matches are displayed here in the middle. So the way these matches are organized, at the top, you have the best match, and then the second best, and so on, all the way down to 10. And if we wanted to compare these, what we actually could do is compare 2 instances. So when I click this, you see it highlights yellow for where that match is. And if we click again, you see a second yellow highlight for the second match. And you see that they're actually quite different, and quite a bit of distance away from one another in the data itself. They're not identical, but this is a shape-based matching. So we're trying to find the actual data patterns that have the closest shape overall. So small differences will affect the rank of these shapes. So the difference is that this shape overall was a better match than, say, the 4th or 5th down. That's the difference. But they do come from different parts on the data. So if you imagine this to be a sensor somewhere, this might represent day 1, and then the next one might represent day 5. So the way that this actually works, and the reason why it's fast, is that we're able to perform a series of approximations of the match. And what that means is, in order to match 2 shapes, you have to find the distance between 2 shapes. But if you can simplify that and calculate that distance in pieces, calculating the most important first, and then the least important last, then you can very quickly tell which shapes are going to be a good match and which shapes are not going to be a good match. So the way that we simplify the matching is actually something that's more or less well known, but the way to organize the matches, the way to keep track of everything, to keep it sped up, was something that we thought of. And when we realized that it would work, it was a great moment, because we knew that we could make it work at the same speed as everybody else, but get that benefit of extra matches along the way. So this is, obviously the world's best method is something that might be in use today, but this is something that generally is not used today. Where this applies is, generally speaking, in the Internet of Things concept, where you have lots of data from lots of different sources, and you're trying to make sense of it. And patterns are a very important way to make sense of that. So I mentioned in the beginning, maybe somebody looking at the subway system, looking at people coming onto the system, and evaluating the load. An operator that is looking at that might be interested in determining how the pickup of people, the increase of people at, say, 5 o'clock, is going to determine delays. So when they look at that system at 5 o'clock with a particular pattern of passengers coming in, they might want to compare the previous days and see how the operators reacted and what kind of adjustments could be made to keep things flowing. So that's one way of looking at this.